convection diffusion model of flood waves is improved with the addition of the third-order dispersion term, in effect constituting a convection-diffusion-dispersion model. With the appropriate dimensional technique, the coefficients of the resulting third-order partial differential equation can be shown to be a function only of the Froude and Vedernikov numbers. This underscores the importance of these two dimensionless numbers in describing the dynamics of flood wave propagation. The convection diffusion model of flood waves is originally due to Hayami in 1951. Doug in 1973 improved the Hayami model by including inertia in the formulation of the diffusion coefficient, resulting in a convection diffusion model with inertia. Doug et al. In 1982 generalized the convection diffusion model with inertia for any friction type and cross-sectional shape. Ponce in 1991 expressed the diffusion coefficient in terms of the Vedernikov number. Froude et al. In 1984 derived the most complete third-order linear equation to date, which includes convection, diffusion, and dispersion processes, to wit, in which Q equal discharge, C convective celerity, nu diffusion coefficient, and eta dispersion coefficient. The convective celerity or flood wave speed is defined as follows, in which A equal flow area. The diffusion coefficient or hydraulic diffusivity for Chessy friction in hydraulically wide channels is, in which Q sub O equal unit width discharge, S sub O equal bottom slope, and F equal Froude number, defined as follows, in which U sub O equal mean velocity, D sub O equal hydraulic depth, and G gravitational acceleration. In most cases of practical interest, the hydraulic depth may be approximated by the flow depth Y sub O. The dispersion coefficient or hydraulic dispersivity is Ponce 1991 has expressed the convective celerity as a function of the Froude and Vedernikov numbers. The Vedernikov number is the ratio of relative kinematic and dynamic wave celerities. Following Doug et al. 1982, Ponce 1991 expressed the diffusion coefficient in terms of the Vedernikov number, in effect generalizing it for all friction types, turbulent Manning or Chessy and laminar, and cross-sectional shapes, including hydraulically wide, triangular, and inherently stable, in which the Vedernikov number is, with beta equal exponent of the discharge flow area rating, Q equal alpha times A to the beta. Given Q sub O equal U sub O Y sub O, and defining a reference channel length L sub O equal Y sub O over S sub O, the diffusion coefficient is Furthermore, with equation 9, the dispersion coefficient is To non-dimensionalize equation 1, we choose appropriate dimensionless variables such as x prime equal x over L sub O and t prime equal t times U sub O over L sub O. Then equation 1 converts to, in which C prime equal dimensionless celerity, nu prime equal dimensionless diffusivity, and eta prime equal dimensionless dispersivity. Therefore, The three coefficients of the dimensionless convection-diffusion-dispersion equation are shown to be only functions of the Froude and Vedernikov numbers. The online calculator onlinedispersivity.php calculates the following wave properties: 1. Celerity, 2. Diffusivity, 3. Dispersivity. Input consists of the following variables: A. Mean velocity, U sub O; B. Hydraulic depth, D sub O, which may be approximated as flow depth, Y sub O; C. Channel slope, S sub O; and D. Exponent of the rating, beta. The coefficients of the dimensionless partial differential equation of convection, diffusion, dispersion of flood waves are shown to be functions only of the Froude and Vedernikov numbers. The Froude number is the ratio of mean velocity to relative dynamic wave celerity. The Vedernikov number is the ratio of relative kinematic wave celerity to relative dynamic wave celerity. The third-order convection-diffusion-dispersion equation may be useful in the analysis of flood propagation problems where both diffusion and dispersion are significant.